Hi students, today we're looking at the other part of the Fundamental Theorem of Calculus and talk about how derivatives and integrals interact with each other. As usual, the assignments that go with this are going to be on your own Jamboard. Alright, so we're going to start off by evaluating the integral in question, and in terms of trying to do this, we need to make some sense of what's going on here. The first thing that we know is that an integral can be described as an antiderivative. So we're looking for the function for whom x squared is a derivative. All right, so if we've got the derivative of something is x squared, we got to think about what that is. Well, I know it's got to be something x cubed, because to get x squared, we're going to use the power rule. So if I think about this, the derivative of x cubed would be 3x squared, but I want just 1x squared. So what if we did 1/3 x cubed? That would be 1/3 times 3, and that would give us just x squared. Cool. So this is going to be 1/3 x cubed. And the second piece of this is I need to find something that the derivative of that thing is going to be 2 sine x. All right, well, I know this is going to have to do with cosine. That would be the derivative of cosine is negative sine x. I don't know why I wrote sing, but that's fun. Okay, so what if I put this negative cosine x, that changes that to positive, and negative 2 cosine of x would give us 2 sine of x. Cool. So then we got minus 2 cosine of x, and I'm going to plug in these values. So we've got 1/3. Actually going to do this in the next line down so we have enough room. 1/3 pi cubed minus 2 cosine of pi. And then we're going to subtract the bottom part. 1/3 of 0 minus 2 cosine of 0. Okay. Calculus-wise, at this point, we're done. We've done an antiderivative here, and we have plugged our values in. If you want to go one step further, you could write this as 1/3 pi cubed. Cosine is the x, pi is here, so that's going to be -1. Negative 2 times -1 is going to be plus 2. Minus 0, and then cosine of 0, that's going to be minus that 2. Oh, that's weird. 1/3 pi cubed is our final answer. Okay, looking at each of these, we're going to do some antiderivatives and then plug some stuff in. We're going to be using these on the next page, so we're not going to simplify these at all. We're just going to kind of work with them. For our first one, we're going to have 3t squared is going to become t to the third, and then minus 6t is going to become minus 3t squared, plus 2 is going to become plus 2t, and I'm going to evaluate this at x and at 2. So x cubed minus 3x squared plus 2x, and then minus 8 minus 12 plus 4. All right, for our second one, we're doing the same thing. So then I'm just gonna take that and then plug in x squared and 2. And I'm not gonna simplify this, and by that, what I mean, I'm gonna say that this is gonna be x squared cubed minus 3x squared squared plus 2x squared, and then minus, that's 2, so I'm just going to say some numbers, because those are the same things we have here. So if we need those, I don't need to recalculate those each time. And then for our last one, this is where we get a little bit more complicated. We're going to end up with that same thing going on, but now we've got x cubed minus 3x cubed squared plus 2x cubed. And then the minus part, this time we don't have a number, so we're going to have to actually plug these in. So I'm going to say the same thing. Instead of x cubed, this time we're going to have 2x all cubed, and then minus 3 times 2x squared, and then plus 2 times 2x. Okay. And again, we're going to need these on the next page. All right, as promised, we're going to have to do some stuff with these on the next page. And for this, we're going to find the derivatives of each of these pieces. So let's do some derivatives now. The derivative of x cubed is going to be 3x squared. Then we get minus 6x and plus 2. Derivative of constants goes away to be 0. Cool, I like it. All right, so we did the antiderivative and then the derivative and got this as a result. Okay. For the next one, doing the derivative, I'm going to do this as 3x squared times the derivative of x squared is going to be 2x. And then we're going to have, okay, that's going to come down, so it'll be 6 times x squared, and then times 2x for a chain rule. And then we're going to have plus 2 times 2x with a chain rule there. I don't love that I ended up in the next space, so I'm going to move the other thing over a little bit. Oh no, come on, you can do it. Okay, there we go. Okay. All right, and then for this one, we're going to have 3x cubed squared, and then that's going to be times the derivative of x cubed, which is 3x squared. We're going to have minus 6x cubed to the first times 3x squared, and then we're going to have times the derivative of x cubed is 3x squared. Okay. And then for the red part, I'll do this down below since I'm out of room. That's going to be minus 3 times 2x squared times 2, minus 6 times 2x to the first power times 2, and then plus 2, and then times 2. Okay. So the goal with these is to kind of factor some of these things if necessary to kind of see what's happening here, because there's something weird going on where when we did the antiderivative of something and then did the derivative of that, something like this happens. So we get, that's what we did to get 3x squared minus 6x plus 2. And to me, that looks exactly the same as the stuff on the inside. Okay. For this one, I noticed that all of these have a 2x attached to the end. I also... Okay, no, we're good. So when looking at this, we end up with times 2x. And when I do that, I get 3x squared minus 6x squared, and then plus 2. And I'd like you to notice that that's the derivative we had here, except where there was an x, now we have an x squared. Okay, so when we did the antiderivative and then the derivative, but put in x squared as part of those bounds, we ended up with that same function that we had before, but instead of an x, we had x squared. And then we had times 2x. And I noticed that 2x has something to do with x squared. In fact, it's a derivative. And we also know that 2x came from doing the chain rule. If we're plugging in x squared and then taking the derivative, it makes sense we have a chain rule for that. And then for the last messy stuff here, the first thing, all of them have a 3x squared as part of that. So I'm going to put that out back. And when we do that, we get 3 stuff squared minus 6 stuff plus 2, which is the same thing that we keep seeing, but now that stuff is x cubed, and the derivative at the end is 3x squared. When we do the other piece, all of these have a 2 at the end, so I'm going to put a times 2, and we've got 3 stuff squared minus 6 stuff plus 2. In this case, that stuff is 2x. Oof, I barely fit that in there. If only I could have like zoomed in or something, which I could have, but instead chose to write really small. That's an interesting thing to notice. So we ended up with the exact same thing as we started with, but we're plugging in these new pieces, and occasionally, when we have 2 of them, we end up subtracting them. The other really important thing to notice, and I kind of skipped over it for the second piece, was that the derivative of a constant is going to be 0, so that if we have some kind of a numerical thing to plug in, we end up not having to deal with that. Okay, so this is the other part of the FTC. I often call this the FTC derivative, and what this is asking us to contemplate is what happens if we take the derivative of an antiderivative of some other function. And I'm actually going to switch the letters up here to make this a little bit more standard. I'm going to call this g and h and call this f of x. Except that for notation purposes, we're going to switch this to f of t so that we're not plugging x into itself. Okay, I'd like us to think about this, and we often don't show this step, we skip right to the end, and that's okay, but we're thinking about this as the antiderivative of f of t evaluated at g of x and h of x. And if I erase my other bracket, so we're taking the derivative of f of g of x minus the derivative of f of h of x. And we should see our chain rules pretty clearly there. So doing the derivative, and again, this is the part we usually skip to, the derivative of big F of x is going to be little f of x, plugging in that upper bound. But then we have a chain rule, so we got to do times g prime of x. Minus, again, the derivative of capital F is lowercase f of h of x times the derivative of h of x because of the chain rule. Often we're only going to have one of the two of these things to plug in, so we don't have to deal with both of these at the same time. So for example, looking at the one that we have down below, using this shortcut, I'm going to end up back at our original function, which is the square root of stuff squared plus 1. And in here, I'm going to plug x. I'm not going to worry about the bottom because that would be a constant. And the derivative of x is 1, so we don't really have to do the chain rule, but if you want, you can put times 1 there anyway. For the second one, we're finding f prime of x when f of x is defined this way, so we're taking the derivative here. That's the same thing we're being asked to do. This is the derivative of an integral of some function. So it's going to be that original function. So 4 stuff plus 1. It's going to be x plus 2 plugged in for the upper one. And then we've got to minus the lower one. So that's going to be, again, 4 stuff plus 1. And in there I'm going to plug x. Neither of those need a chain rule because the derivative of each of those pieces is 1. We could simplify that, but we don't need to.